waves. We've navigated to the waves part of the topic, the waves topic part of the database, and if we look down here, we've got the simulations here. Wait a second. Let me just pause that. I'm just going to change that there. So I think the first thing we're going to maybe start a few different simulations here, and we can just dive in and play with a few of them. So the way to start the simulations is by clicking here. Now, if I click on that like that, it'll just it actually does open up a new page. Sometimes it will not do that. I think if I press Control, come on, doing it. So the way to load it up on a separate page, if we wanted to, is to click on that and then hold on to Control, and it opens it up in the background over there, and then we can look at them in a moment. So let's open up that one as well, and we'll open up. There's another 27 simulations to look at over there. Polarization is something you'll look at A level. We're not going to look at that just yet. We'll open up this thing about one of the things to do with the eye. And we'll open up this one and this one. I don't know what that one's going to be about. It doesn't have a picture. Let's open up the sound one as well. I think that will do for now. Maybe that one as well. And that one. It's got quite a few. I can give you links to all these in a moment, maybe. So let's start off with this one here. This is the classic one I always start off with when I'm teaching waves. So this is just called Wave on a String. You can find it just by Googling PHET. And I'm going to pause the simulation first. I'm going to choose No End. I'm going to choose Oscillate. I'm going to turn the damping down to none. And then I'm going to press play. So we got our wave, right? Now you can turn it on slow motion, or you can let's leave it on slow motion. Now what we have here is a type of wave called a transverse wave. Now, can you remember what a transverse wave means? What does transverse mean? So we've got to be careful about how, when we say a wave that travels perpendicular to what? Sorry. Better. So basically what you're looking for, the word you want to be looking for is oscillation. Oscillation is basically the direction that this motor is going. It's also the direction that any of the particles are going. So if I press play now, and if you look at this green circle, it's only moving up and down. It looks like something's moving from left to right, but the thing that's actually that we're looking at that is moving from left to right is nothing but a pattern. The pattern itself is moving from left to right, but the solid matter, the solid stuff that the wave is traveling through, that is only moving up and down. The string itself is moving up and down, the motor's moving up and down, and so that's the thing that is moving or oscillating. Okay, so when we talk about transverse wave, we say that the oscillation is perpendicular to the direction of the wave, or if you want, I'm trying to perpendicular, write and talk at the same time. It's a bit difficult. So oscillation perpendicular to wave. A good word to use is propagation. So the wave propagation is from left to right. It just means what direction is the wave moving. Okay. You can also say what direction is the energy moving, because waves are always a movement of energy from A to B, from one place to another. So it's the wave propagation is going from left to right, or we can say the energy transfer is going from left to right. It's always a type of energy is moving. In this particular case, it's kinetic energy. Okay, so we're moving. We're causing movement. If I reset it and press play, at the very beginning, none of this is moving over here. This started some movement, and it sends the energy from left to right. So the thing that's moving from left to right is energy, or if you like, a pattern. Okay, so you can do that anyway. So that gets that across. Now, a good way to remember transverse is if you keep on to get that thing there, is to draw the arrow there. We can say that's the oscillation, and then that's perpendicular. So that's the wave propagation. That is obviously a right angle, but it looks like a T. So you can write transverse. But you remembered it anyway, so you probably won't need that way of doing it. Now, if I were to change the amplitude, looks like we can turn the amplitude up and down. How might this look differently on the simulation? Right, good. Yeah, good. You're quite familiar with that. And frequency, tell me about frequency. Per second. So the frequency is the amount of waves per second. So if I put that, then this thing starts to go up and down more quickly, more often, right? More frequently. Now, it tends to be that the frequency, when you increase the frequency, you decrease this distance. What's this distance called here? Right, good. So the distance from one place to another, the wavelength, that will decrease when you increase the frequency. Okay, we won't bother making too many notes like this because I won't bother defining amplitude and frequency because you clearly remember all that fairly well. But we'll just make sure that we understand the basics. You probably know that to measure the amplitude is from there to there, right? And do you know why that is, though? Do you know why you don't do it from the bottom to the top? A lot of people, it gets usually taught at school that that's what you do, but it doesn't. The understanding the reason why is often confusing, especially if we imagine we drew like a surface of water. This is how they often catch you out in exams. They'll drew a water wave like that, and then they ask you to do the amplitude there, and you might say to yourself, "Oh, I know not to do it from the bottom to the top, so you do it from here." That's wrong, isn't it? So you'd actually do it from here because it's the middle point. What's significant about the middle point is if there was no water wave, that's where the water would be normally. So the amplitude is the distance if it's a visible wave like a water wave or where the amplitude is measured in distance, then the amplitude is the difference between where it would normally be and where it is, or the maximum. At GCSE, at A level, you're going to be using the word displacement. How much it goes from here to here, that means that particle has a certain displacement. Amplitude is the maximum displacement from its rest point, from where it would be if there was no wave. If I reduce this amplitude down, then it gets closer and closer to the middle line. Eventually, if I had an amplitude of 0, then it would just be on the middle line. So there's no amplitude because it's not gone above where it would normally be. This thing is still going around 3 times a second, but it's not actually adding any. It's not doing anything. So the amplitude is how much more above or below it would normally be. Now remember that this is a wave of this is like a mechanical wave that has the amplitude is measured in actual distance, but it doesn't need to be that way. A sound wave doesn't change. It's actually measuring the thing that's changing is actually air pressure, right? So we're still going to be, if we drew a graph of how things are changing over time, then the thing that's changing this time would be air pressure. If it's electromagnetic wave like light or infrared, the thing that's changing is the electric field or the magnetic field. This you'll be doing more of when you go to A-level. You haven't really done it at GCSE, but essentially that is what electromagnetic field is. Something is changing as you go from A to B. If this is a wave on a string, but if this is an electromagnetic wave, then at this point there is no electric field, and at this point there's maximum electric field, okay, or magnetic field, okay. With a sound wave, maybe it's a graph of air pressure against distance, right? Does that sort of make sense? I'm kind of speed teaching that little bit because I wanted to give you an overview of waves in general. So also at A-level, you're looking to damping. Let's briefly introduce what damping is. See if we can work it out. Notice on the left-hand side, it's still got fairly high amplitude, but yeah, go on, define it. Exactly, yeah. So in reality, there is damping, isn't there? In everyday life, there's damping. If I wouldn't be, if I did that, I wouldn't have the same amplitude on the right-hand side as I do on the left. Energy gets lost, so there is actually damping. Sometimes there's more damping, sometimes there's less. It depends on energy loss in the system. It depends on how much friction there is in the rope or whatever it might be, right? Damping's not the same as spreading out either. So in this case, we have essentially a one-dimensional wave in a sense. Like the direction of the wave is only going from left to right on a string, whereas on a sound wave, it's going in 3 dimensions. So as it spreads away from the source, the energy is dissipated and spreads out in 3 dimensions. So the amplitude of the wave gets less and less the further away you get. That's not really damping in that way. That's just it spreading out. And damping would be more like something's absorbed that sound energy in some way. So that's one good way to introduce waves. So what I'll do is I'll take a snapshot